All right. So what we're wanting to cover today is we're wanting to follow up on the previous lecture that we did last Tuesday, where we introduced some bits about error analysis and uncertainty. So we want to expand upon that a little bit and then actually step through a few examples of sort of what you should be doing on your report. So one thing that we brought up when we were specifically talking about random error in the last discussion, we said that what makes it random is, it's random error follows a statistical distribution, but we didn't really ever explain what a distribution is. So we want to cover that now. So basically, a distribution is you've probably heard of several types. You've heard of a Gaussian, you've seen a bell curve, and that's a distribution, right? And what it is it just gives you the relative chance or the probability of getting a specific value when I take one measurement of a quantity. That's what it means in this context. So every time I make a individual measurement, I'm basically picking a random value off of that distribution. And as I make more and more measurements, I'm basically going to continue to pull values out of this distribution until I should be able to get to see the shape of this distribution, right? So a lot of times before you take your measurement, you don't necessarily know what type of distribution you expect the data to follow. You often and will assume a normal or a Gaussian distribution. So, and when I talk about multiple measurements, I'm talking about multiple measurements of the same value, right? I wouldn't expect two different measurements to be related at all. So I don't want to treat them as a single distribution, right? So for example, we're talking about repeated measurements of the frequency at a single temperature. So if I can see the full distribution, if I know what it is, I can see the relative likelihood and how those values, how the probability is distributed over all the possible values. But like I said, this distribution is the random error. And when I just draw a smooth curve, I'm usually assuming that I'm ignoring the systematic error, right? Or I'm assuming it's small compared to the random error. So like I said, the most common distribution you will run into is the Gaussian distribution. It's the normal distribution. It's often called a bell curve, right? You can see that it has this particular shape, right? And if you were to look at the formula for it, it would have this form given by this equation here, right? And you'll see that there's basically three constants in this equation. So P, the result of this is the probability, right? So, and X is the particular measurement value, right? So if I plug in X to this equation, it gives me the probability I would get of measuring that particular X. So like I said, there's three different constants here. And you can see there's this K out in front. There's this circle with a line, and that's a lowercase sigma. And then you can see this mu in the denominator of the fraction of this exponent. So what each of these do is they will control the shape of this distribution. In particular, mu is the mean, the Gaussian distribution is a symmetric distribution, right? It has the same shape above and below the mean. So all that mu does is basically shift the entire distribution to the left or the right. So that mu is whatever that value is right at the peak. The sigma is the variance, and that is how wide this distribution is. And when we talk about the random error, we are specifically talking about the sigma, and you may also hear that referred to as the variance, right? So if sigma is a larger value, it will be wider. If it is a small value, you'll have a very, very narrow peak. And in fact, if you were to, think about what would happen as sigma went to 0, basically this thing would go to a single vertical line at the mean, which means like, oh, I'm only ever going to get this one possible value because I've been able to reduce my random error so much. Like I said, the height at any particular value, the P of X, is just how likely we are to get that value. And the constant K out in front is just what you call a normalization, right? So if I was to add up all the possible probabilities, it should equal 1, right? Because when we talk about probabilities, we're talking about the fractional chance of getting something. So if I add up all the possible values, it should be equal to 1, which means 100% chance of getting a value on this distribution. So you can see here, this is basically just an arbitrary example of what this should look like. In particular, you can see that for this case, the mean value mu is at 10, right? It peaks at 10. In particular, the sigma is 3. And then I've gone in here and shaded in the regions 1 sigma and 2 sigma from the peak. And usually, those are sort of important values because that green region, the region that is within 1 sigma of the peak, contains 67% of all the possible values. And the green plus the blue region contains 95%. So what a way of saying that is I have a 95% chance of getting a value between 4 and 16 for this particular distribution. Now, there's a key thing to realize about this mean here, right? This is not the mean of your measurements. This is the mean of the underlying distribution that you're randomly taking samples of, right? So if I was to take an infinite number of samples, I would be able to measure that mean, that mu value. Instead, what you are actually measuring when you average a bunch of values to is the mean of the sample, right? And the formula for that, you may have not seen it in that notation, is exactly what you think it is. You add up all the measurements and you divide by the number of measurements, right? But the point is that is really just an estimate of that that true mean, that distribution mean, right? Unless I take 10,000 measurements, it's not the actual mean. It's just what is my best guess of what mu is based on the measurements that I've taken. So this helps us put into context a little bit better of those standard deviation formulas that we talked about last time. So, one thing that you want to be careful of is if you say standard deviation, which of these three formulas that are usually called the standard deviation do you mean, right? Because in different practices or in different fields, some of these will not be, different. If a different assumption of the standard deviation will be used, right? So for example, when you're writing your report, if you use the standard deviation, you want to be explicit and show that equation in your report so that everyone knows which version you're talking about. And in general, these are what's called the population standard deviation, the sample standard deviation, and then the standard deviation of the mean. And this is also important because if you're going to use the equation in like Excel or some other software, if you type in standard deviation, you want to look and be aware of which one this is. So this version of the standard deviation, the population standard deviation, is basically assuming that you have the entire population of the samples. So, for us, that's not really applicable because what we're talking about, the population, is that's all possible measurements, right? But if you were actually doing demographics where you have like my entire population is these 450 people, that's where you might use it. But because when we take measurements, we're basically taking samples, this is not the version we want to use. And you'll notice basically the only difference between this one and the sample standard deviation is that n-1 is on the bottom. So one thing you want to note is, well, actually, if I take a large number of samples, n and n-1 are pretty much the same thing. There's not a lot of a difference of dividing by 1,000 as opposed to dividing by 1,001, right? So as n becomes large, that -1 doesn't really matter. And what that means is as you get a larger and larger sample of the population, those two standard deviations become the exact same thing. So this is what you're going to want to use when you're talking about samples. And another thing to look at here is if I take a single measurement, right? That means my n-1 is just 0, right? Because 1 minus 1 is 0. And also that means my average, my mean, is going to be equal to that same value, right? So that means if I plug this in to this equation, I get a 0 over 0, which is undefined. That's something meaningless mathematically, right? But that sort of makes sense if you think about it, because if I just take a single measurement, there's nothing I can really be able to tell about the distribution from that single measurement. I have to take multiple measurements to be able to say anything. And then finally, the third standard deviation that you'll run into, and this is one you probably want to be using in your report, is the standard deviation of the mean, right? So for the other two standard deviations, you're estimating how wide that distribution is. You're saying how much is my single measurement off from that middle mean, right? Where in this one, what you're actually measuring is how close your average, the average from your measurements, is to the true standard deviation, or sorry, the true mean, to that peak value. And one thing to note is the population and the sample standard deviation, what they're going to go to as I take many, many measurements is they're going to go to that that regular sigma. They're going to eventually approach this value here and tell you that width. But what will happen to the standard deviation of the mean is it will go to 0 because your sample average, the average of your measurements, is going to be a very, very accurate estimate of what that true distribution mean is. So that means if, for example, I am taking the average of several frequency measurements at a single temperature, and I'm going to use that mean value on my plot. If I want to estimate the error on that point, which is an average of several individual measurements, this is the equation I'm going to use. So how do you go about actually calculating this? So this is basically an example of how you would do this in Excel. You know, depending on what other software you're using, this may be a little bit different, but I figured this was the most commonly used thing for students at this level, what you would probably be using. So let's assume, you know, I took 5 measurements of the temperature of the water bath with the assumption that these are repeated measurements of the same water bath that's at the same temperature, right? And my thermometer, I've got a pretty decent digital thermometer, and it reads out into 1/10 of a degree. So, and I did this 5 times. So first thing I want to do is I want to calculate the sum, right? So I'll add all of these values up and I'll calculate the sum. Also, I want to note that I've taken 5 values, right? That's what the n is here. I then want to take the average of those 5 values. That's pretty simple. I just divide that total value by the number of measurements. Fairly simple. And then I want to subtract the mean from each one of these, or I could subtract each one of those from the mean. It turns out it's not going to matter because I'm going to square all of these. So if I get a negative, all that would happen would be the difference between those two is a factor of -1, right? And when I square it, that just goes away. So I'm going to take my average, which is what this B9 is, and I'm going to subtract it from each individual value, right? So you can see that, okay, 35 minus 34.94, 0.006, right? And I'm going to repeat that for every single one of my measurements. Okay, and then I am going to square each one of these values. Fairly simple. Take the number, multiply it by itself. And then I am going to add up the sum. So I'm going to just add up all of those squares, right? The sum of the squared values. And then I divide that by n-1, which in this case is 4. And I get a standard deviation. So right now I have not taken any concerns about significant figures or reporting or rounding. You know, I've just plugged the numbers into Excel and I get 0.180, right? Oh, sorry. I forgot you have to take the square root. It helps if you go through the entire equation. So that is what my standard deviation of these 5 samples is, right? But I don't really need to go through that, at least in Excel and most other data analysis software. They're going to have the function built in. So, you know, it'll be named something like standard deviation, and you'll just select the 5 samples and it'll give you the value. But one thing you need to be careful of here is you will see that there's stdev.p and .s, right? So as you might be able to guess, that's our population standard deviation and our sample standard deviation. So like I said, you want to be careful and explicit about which standard deviation you are using. And if you click on the help for each of these functions in Excel, it should give you the explicit equation so that you can tell what you are actually calculating if you're not sure. But you can see that basically, if I use the formula or if I go through step by step, I get the same value, right? I get this 0.3286, etc. So if we did the measurement instead with like a bulb thermometer, where I can only read out, say, half a degree. So, assume I did 5 measurements that way, and every time I did it, it would look like 35, right? 35, 35, 35. If I repeat all my calculations for that, I will get a standard deviation of 0 because, right, they're all the exact same value. They're all exactly equal to the mean. So you might want, that might lead you to think, oh, well, the error is 0, right? But that's not really accurate, right? This goes back to what we talked about of, hey, there's actually 2 kinds of error. There's random error and there's systematic error, right? Another way to think about this is, hey, if I measure the length of a metal bar with a ruler that's marked out in single millimeters, right? And I measure, and I see that it reads exactly 12 millimeters each time, right? If, again, I would calculate the standard deviation, I would get 0 because it read exactly 12 every time. So that means, does that mean that I know that bar is exactly 12.00000 as many decimal places as you want? No, because like we talked about, and I've said a few times, there is also a systematic error. So since, the ruler is only marked down to these increments, we would probably estimate that the systematic error, the resolution can't be better than 1 millimeter, right? So that means you have to not only calculate your standard deviation, calculate your random error, you also have to come up with some estimate of what your systematic error is and add it to the random error, right? Because they're both contributing to the total error. And the reason that I get 0 for my standard deviation in these cases is that the increments and the steps of the measuring device are much larger than the width of my distribution. Another way of saying that is my systematic error is large and it's dominating, and you could even say it's masking your statistical error. So the next question then becomes, well, how do I add errors, different types of errors together? So the simplest solution would be to just simply add them. Total error is systematic error plus random error. And then also, this is more general. It doesn't have to just be random and systematic. This could in fact be error from one part of the measurement and error from a second part of the measurement. For example, yeah. But in general, we don't expect these errors to be at their maximum values at the same time. So the general practice is to use this particular form of addition That's called adding in quadrature. But all it means is you square the two errors, add them together, and then take that square root. Now, there is a strict mathematical justification for this that you could prove. We're not going to do that here. That's well beyond the scope of what we want to get into in this program. But one thing to note is it sort of assumes that our 1 and our 2 here are independent of each other. They're independent variables. They don't affect each other. And that each of those errors follows a normal distribution. So, an example of this is going back to the numbers that we calculated before. If we take the random error, square it, and add it to the system error squared, and then take the square root. So in the event of our bulb thermometer where our random error was effectively 0, and we add that to our systematic error, which we, in this case, estimated to be 0.5 degrees C, based on the fact that I can read out half-degree increments of the thermometer. If I do that, I will see that it is 0.5 C. But if I take the example with the digital thermometer, I can see that if I say the systematic error in that case is 0.1, and I add that to my random error, which is actually larger and significant now. So I'll get a total error of 0.3 and a half C almost. So this is why last time I sort of talked about you want to figure out how many measurements do I need to take such that this random error gets to be about the same size as the systematic error, right? Because once it gets to that size and maybe a little bit smaller, my total error is pretty much just going to end up being close to my systematic error. I can take measurements all day and get that error down to 0 if I'm averaging multiple get the random error down to 0 if I'm averaging multiple measurements, but I'm going to have this systematic error, which is at some fixed value depending on my setup, depending on my measurement devices. So one thing that is useful is you can generalize that addition of error. And this is something that's called propagation of error. And what this is used for is if you are, say, calculating some final value, which we're just calling this F here, based on a bunch of other variables, right? An example of this, I could be calculating the volume, in which case I would have length, width, and height if it's a rectangular prism, right? So I'm not directly measuring the volume. I'm going to measure the length, the width, and the height. So I want to know how you calculate that error in the volume based on these are the errors I had for those other 3 dimensions. So again, this has those same assumptions where they're not each one of my variables is independent of each other, which will be the case a lot of times. And I'm again assuming they follow a normal distribution, right? Which is usually a good starting point. So unfortunately, this requires calculus. So for those of you that aren't familiar, each one of these terms here is the partial derivative of that function f, right? So this would be like the partial derivative of the volume. And what the derivative is, I'm trying to see how that quantity changes with respect to that. So unfortunately, if you don't know how to do that, if you don't know how to take derivatives, you'll probably need to look up some, if you have something like this, you'll need to look up an equation for what the total error is. And on the website, we have a few examples of, hey, here's how to calculate the total propagated error if you have this type of function, right? So each one of these sigma x1, x2, those are the errors in the individual measurements that you're using to calculate that final value. And one thing I would point out is this is not a calculus class. This is not a math class. We don't care if you need to look up the derivatives. You know, if you don't try and rack your brain trying to do a complex derivative. Look it up in the table or use the resources available to you. So as a quick example, this is how you would do it for something that's simply a product, right? So we're talking about the volume of a rectangular object. It has a length, a width, and a height. So hopefully you guys are familiar. The equation of volume for a rectangular prism is just the length, the width times the height, right? So if I plug in my 3 measured values, 10 times 12 times 50, I would get 600 cubic millimeters, right? And now let's say the error for each one of these was dominated by the systematics, and it was 0.5 millimeter each, right? Which you could probably see if I'm doing this with like a ruler, you know, maybe I have a ruler that's marked out such that I can estimate 0.5 millimeter increments, right? And I'm probably not going to be able to see any random error in that case. So now I need to calculate all of the partial derivatives so that I can calculate my total error. So the volume is a function of these 3 variables, length, width, and height. Those are like my x1, x2 in that earlier generic formula. So my formula for the error in the volume is this first equation right here, right? So I need to take the partial derivative of volume with respect to length, width, and height, right? And multiply each one of those times the right error. I square them all together. So either by knowing the derivatives or looking it up in the table or a table, I can look up, okay, the partial derivative of volume with respect to length is the length just goes away. I get width times height, you know, length times height. And I'm sorry, I need to correct this. This should be length times width on the third one. So if I plug these in, I get an equation like this. So I get the width times the height times the error in the length, right? So this is just a restatement of that equation. But one thing you want to note is each one of the terms in these parentheses has units of volume, right? Width has units of millimeters, height has units of millimeters. Well, the error in length is going to have the same units as error, right? It's going to be 10 plus or minus 5 millimeters, right? So each one of those terms has units of volume. So if I plug in the appropriate errors and I do that equation, I'm going to get a total error of 71.5 millimeters cubed. So, and the way I would report that is I would probably round the error off to a single significant figure. So I'd round it to 70 millimeters. So like I said, we have a handout that has a few examples of the propagation of error equations that says if you have an equation like this, this is what the formula for the total error is. So one thing that I've sort of mentioned without justifying is, well, we usually just assume it's a Gaussian distribution. Well, why would we assume a Gaussian distribution, right? So in the event that I have a large number of measurements, a large number of possible values, basically almost all of the other distributions will start to appear and approach becoming a Gaussian distribution, which is convenient because there's a lot of useful math for handling propagation of error on a Gaussian, right? All of those propagation of error formulas that I covered earlier assume a Gaussian distribution. So, and like I said, usually a Gaussian distribution is a good first guess for most physical measurements. And in fact, you can mathematically prove that basically if I have a bunch of if I have a very large number of small errors of random different types of distribution, it doesn't really matter what they are. If I have a whole bunch of these contributing, the total error will eventually look like a Gaussian. And that's something called the central limit theorem. It's statistics, it's math that we don't really expect you guys to know or cover. It's just, this is more just for your own information, that is something that exists. So now that I know how to, in theory, calculate an error, we want to talk about, well, what is the correct practice for reporting that error? So, for example, if I think the error is 0.5 millimeter, right? It doesn't really make sense for me to report that average value out to the 1,000th of a millimeter, right? I've said that all of my uncertainty is this big. So these other two decimal places are much smaller than my uncertainty, and I can't even really be sure about it, right? So usually the practice is you round your error to a single significant digit or maybe 2 significant digits. And then I round the measurement to whatever that largest decimal place is. So for this example, I round my error to a single significant figure. The 0.5 is my significant digit, which means I'm going to, and that is in the 10th place. So I'm going to round my measurement to the 10th place, right? So I'm going to explicitly use this decimal 0.0 to show that that 0 after the decimal is significant. One thing you want to be careful of, though, is don't round prematurely. Don't round intermediate values that you're using for calculations. Because if you can do that, basically your rounding error can get bigger and bigger as if you were to round off every single step. But the most important thing is you want to be explicit on how you did that error calculations, and to avoid confusion, just say what you mean with your plus or minus, right? I want to say, hey, that plus or minus is the error which I calculated like this. So now I just want to sort of step through an example of how you would apply this. So first, let's assume that I did a bunch of temperature measurements and I was using a bulb thermometer. So it's again where the random error in the temperature is small. I'm assuming the total error on the temperature is 0.5 from the resolution of the bulb. So if I now measure the frequency, so I've taken 5 frequency measurements, and if I, based on the software I was using and the width of the peaks in the software and the size of the pixels, I estimate each one of those peaks for the harmonics is about 11 hertz, right? So now I have 5 independent measurements of the fundamental frequency, right? So I measured the first peak and the second peak, and I took the difference of all of them, right? So I calculate the mean, the standard deviation of this sample, and I calculate the standard deviation of the mean. And like I said, I have estimated my error to be, my systematic error to be 11 hertz. So if I add my random error, which is the standard deviation of the mean in this case, that 8.55, square it, add it to 11 squared and take the square root, I'm going to get a total frequency error of 13.9. Or I would probably round that to 14 if I was reporting it as a final result. Yep, so sorry, this is just reiterating what I just said. I calculate the mean of my 5 measurements to get that mean value for my point. I calculate the standard deviation and then the standard deviation of that mean, and then I add my errors together. So the way that I would report my first data point is it would be, sorry, I have not correctly rounded the hertz here. So I would actually round that to 1260 plus or minus 14 hertz, right? And then 995 plus or minus 0.5, right? And that gives me a single data point that I would then be using to plot or do analysis on, right? That I've averaged these 5 points together with. So I would repeat a similar process to all of the repeated measurements of the same temperature. So in this case, I've taken several temperature repeated measurements at basically from 95 down to 5 degrees. This gives me a set of X values and Y values, each with their own individual error, right? Which I'm going to use to show as error bars. I have an error in temperature for one of these and an error in frequency for each one of these. So if I probably would use a scatter plot like this. So I'll select all the points, plot them in Excel. And in this case, I'm plotting my frequency on the x-axis and my temperature on the y-axis. So one thing to note here is this is stepping through how to plot this graph. So that's why I don't have things like units and axes labels yet. But when you get finished, all of that stuff should be on your plot. So now I want to add error bars. And in this case, I'm assuming that the positive and negative error is the same. In Excel, there will be an option to independently specify them. But what we want to do is select the option that lets you pick error points, not the one. So there's going to be in Excel like an option to do a percentage, which is not what you want to do, or a fixed value, which would basically be the same error for every data point. So what you're going to want to do is add a horizontal and vertical error bar to each one of these points so that you can show it. And depending on the size of your error bars and the size of the data points, you may need to adjust the size of this marker so that you can actually see your error bars. Or alternatively, you may want to specify in your caption that the error bars are small, so you've left them off for clarity. So if I've done this a bunch of times, the next thing that I would probably want to do is try and add a trend line. Well, you can see from this particular plot, that's definitely not a linear relationship. However, if you go through the data sheet, you will be able to figure out, be able to predict individual values. But in this case, I may just want to see which of the various, trend line functions match the data the best. So I could try a few of these, a polynomial, a logarithmic, I'm in this case, I'm just sort of trying to look and see which one of these matches the data, which looks like it matches the data. Ideally, though, you would have some expectation, in this case, by looking at the data sheets and what that RTD is supposed to do. You should then have an idea of, oh, this is what the data should actually look like. And then an important thing is, if I'm going to have this trend line on there, I in general want to show that equation on my plot. So once I've done all of that, I want to do all my remaining steps to make my plot readable. I want to add axes titles. I want to add units, probably a title. I'm going to then want to try and make some conclusions on how well does that data match my plot. So we expect about 2/3 of our points error bars to overlap our line if it's a good fit. And that comes from all the way back here in the second slide, where we expect about 2/3 of the measurements to lie within there, that 1 sigma version, that 1 sigma region, because the error bars should be a representative of 1 sigma. If many of the points don't match, or if there's way less than 2/3 of the data points, that means it's probably not a good fit function, or I have made an error in my error estimation. Either I underestimated my error, maybe I missed something. But also, if I have, way more than 2/3 of my data points, for example, if all of my data points lie perfectly on the line, that might mean a few things. One, I might have too many constants in my fit, right? So like that's called overfitting. And as we talked about last time, if I pick a polynomial with enough constants in it, I can always make that polynomial go exactly through every one of my data points. But it could also mean that you have overestimated your error. And one thing in particular is, those specs that you're going to get from like the manual of the multimeter are sort of upper limits, in that the manufacturer guarantees the multimeter will be at least that good, but it's probably a little bit better than that. So they're not really trying to give you a scientific error. They're saying this is the minimum accuracy we guarantee. So what that'll mean is probably the actual error is a little bit smaller than that specified value, but you don't really have a good way of telling that, unfortunately. So that is it for the lecture.